A hot object radiates. That's what we discussed. Everything radiates, as long as it's warmer than the surroundings. For a dense, dark object, so for an object that essentially absorbs light that hits it, such as you, me, the Earth, and it turns out the sun, the radiation is almost completely characterized, and it's precisely completely characterized for some idealized black body, an object that absorbs any light that falls upon it, by the temperature. It turns out that the nature of the radiation produced by a warm object, if it's dense, is essentially a property of light and thermodynamics and has nothing to do with the object itself. And this is called blackbody radiation, and it has two important properties. One is that hotter objects are blue. This despite the fact that blue is a cold color and red a warm color to our intuition. It turns out that hotter objects radiate shorter wavelength. In other words, a blue glow is hotter than a red glow because a red glow has a longer wavelength. This is summarized in Wien's displacement law, which says that the wavelength at which an object emits more radiation than any other wavelength, the wavelength of maximum emission, multiplied by the object's temperature, is actually a constant, so that if you double the temperature of an object, the wavelength at which it emits is halved, and Wien's constant is written over here. It's got units of meters times Kelvin, so wavelength times degree. The other and more familiar statement is that hotter objects produce more light. This is encoded in the Stefan Boltzmann relation, which tells us that the rate at which each meter squared of an object radiates, of course a big object radiates more than a little object if they're the same temperature. 2 light bulbs make more light than 1 light bulb. So we need to normalize to the rate at which an object produces radiation per meter squared, that's F in watts per meter squared, and the rate at which each meter squared of an object radiates is proportional to the 4th power of the temperature in degrees Kelvin, and so doubling the temperature leads to a 16-fold increase in radiation, and the constant, the Stefan Boltzmann constant, sigma, has this numerical value in our units, and its units are watts per meter squared per degree Kelvin to the 4th. Let's take a look at what this blackbody radiation looks like. Here we have a plot of the relative intensity in various wavelengths as a function of the wavelength from near zero to a few times 10 to the minus 6 micrometers, and so the visible band is located over here, and the blackbody curve has this characteristic shape. As I said, it's independent of the material, and the curve I've plotted here is the curve for an object that glows that has a temperature of about 3,000 degrees Kelvin. 3,000 degrees Kelvin is about the temperature of the filament in an incandescent light bulb. And what you will notice is that most of the light produced by an incandescent light bulb's blackbody radiation is in fact not light. It is invisible to us. It is infrared radiation which heats us. If you talk about people not liking incandescent lamps as being very inefficient, this is because, due to limitations of the filaments melt if you heat them too hot. Most of the light produced by an incandescent lamp is in fact not light, it is just heat. And so, on the other hand, if we heat the object a little bit, this is an object with a temperature of, say, 6,000 degrees. This is closer to the sun, and you see that much of the light produced by the sun is in fact in the visible spectrum. It's very nice of the sun to be adjusted to our atmosphere so that much of the sunlight can in fact penetrate our atmosphere and we can use it to see. And you also see that the factor of 2 in temperature leads to this huge increase. The previous light bulb's graph has been scaled down here. It looks very small. Remember, doubling the temperature increases the total radiation by a factor of 16. And it has also moved the maximum from, according to Wien's law, from the infrared, in this case, down into the visible. And we can add another object, say, with an even higher temperature. Let's say 12,000 degrees, so another doubling. In this case, the spectrum, again, increases to the point where the sun spectrum is negligible, and the peak is now in the ultraviolet. So we're seeing Wien's displacement to the left. Hotter temperatures mean bluer light. We're also seeing the Stefan Boltzmann law in action. Hotter temperatures mean way, way, way more light. These are all important observations. Let's see what we can do with them.